Hello, my name is Bob D. Hilster, and I am your particle model guru. Today's video is on electromagnetic radiation. By the way, if you're new to TPM, the particle model, I suggest you watch these two videos, the particle model overview and levels of the universe. Once you watch these, you'll have a better understanding of what's involved with the particle model, and it should then be easier for you to understand any individual video, since I can't cover everything in one short video. Well, I had a recent request by a gentleman named Aidan, and he writes, "Please attempt to explain the mechanics occurring in radiation using the particle model." So thank you, Aidan. Appreciate your request. I'd like to respond to viewers who make requests or ask questions. Of course, you know that radiation can come in many different forms. And Wikipedia has got all of them listed, or it seems like all of them. It states in physics, radiation is the emission or transmission of energy. It's the transmission of energy. Of course, energy, according to the particle model, my interpretation is not real, but this not real energy is in the form of waves or particles through space, through open space, or through a material medium. And these include electromagnetic radiation, which is the only thing I'm covering today. And that includes radio waves, microwaves, and the whole spectrum from radio rays up to gamma rays. Particle radiation, which is alpha radiation, beta radiation, and neutron radiation, each one a particle. There's acoustic radiation such as ultrasound, seismic waves, and physical transmit through a physical medium. Interesting enough, water waves are not mentioned here. Gravitational radiation, radiation that takes the form of gravitational waves or ripples through the curvature of space-time. Yes, this type of radiation is something that the particle model does not agree with. And here's a picture from the same Wikipedia article showing alpha particles, which is 2 protons and 2 neutrons that can't even go through paper. Beta particle is stated to be a high energy electron, whatever that is, goes through paper but can't go through aluminum. Not so sure about that one. Particle model, it should go through aluminum. I'm curious now as to why they say it stops. And then there's the gamma radiation, which is the whole electric spectrum, and it goes through paper, aluminum, and not much of it, but some of it gets through lead. It's just a visual of what the types of radiation. And this is energy. Energy is what they say it is. The electromagnetic wave is also shown as the motion to the right direction, that apparently velocity c, that has an electric field and a magnetic field. And that electric field is oscillating. It's a blue arrow, and you can see that it goes up and then down and then up and down. And at right angles to the electric field and to the velocity is the magnetic field, and it decreases and increases, decreases and increases. It's an oscillating electric and magnetic fields. One thing that's never explained: what makes this go up and down? What makes this decrease and increase? It just says it doesn't. That's what it does. No explanation. But the particle model, when I got started with trying to explain electromagnetic radiation, I actually asked this question: can a particle act like a wave? I asked this question in 2015, so this is only 3 years old. It'll be 4 in next year. So I started with one particle with spin, and I couldn't make that work. In particular, white light was a problem. How do you have one particle spinning at one rate generate white light? Doesn't seem to work very well. So then I said, what about 3 particles? Because with white light, you need a sense of, in one sense, red, green, and blue, and out of any 3 particles that are spinning, you could probably create white light. But then I had a problem with how white light reflects off of green grass or brown dirt, and in the images I couldn't make work. Maybe if I tried harder, I could have. But I don't know how I made this logical step to step 3, but now when I look back on it, I might say if 1 particle doesn't work and 3 particles don't work, maybe a stream of many particles work. And yes, I did that. I said to myself, well, what if I had lots of particles that made a peak? Then I had fewer particles that make a valley, and then followed by lots of particles with a peak. All of these particles moving through space at speed c. That was my original thought, very simply stated. And the interesting part is that the wavelength of this stream of particles is defined by the distance between this peak and that peak. And that's exactly the way we define the wavelength. Then it's in meters, nanometers maybe, but still it's a physical dimension. And if you have a peak here and a peak sometime later as it goes through space, you have a wavelength. My first attempt was just a series of numbers. I was trying to make a sine wave, but I said, okay, let's just take 3 numbers. And much later, when I realized it, you plot these numbers using a spreadsheet. It's a triangular wave. Well, what's really interesting about that is it really leads to the notion that whether your distribution emulates a sine wave or a triangular wave or a pulse or a square wave or anything rather unique, very odd shaped wave, this model can do all of them. For example, my son David, when he got onto it and I told him about it, he decided to make an ideal sine wave. And he used the mathematics of a sine wave, and he used it to calculate the spacing of these peaks. And so he's got particles moving to the right at speed c. The fact that you have, I know it's only 4, but lots of particles here and lots of particles here. And in the valley, you have very few, is what you'd have to generate. What nature would have to generate if it's going to make a perfect sine wave out of a stream of particles. Yes, it can be done. And by the way, the intensity of the sine wave, if I wanted a higher intensity sine wave using the particle model, I would have 8 or 100 or 1,000 particles at the peak and very few in the valley. So the intensity of the particle model wave is the number of particles at the peak. That's the number of peak. That peak hits your eye. It hits the red. If this is a red wavelength, that when this peak hits your eye, it pushes on the red cone in your eye. And if there's too many of these particles hitting your red cone of your eye, you actually can damage that, just physically damage by changing the atomic and molecular structure of the cone in your eye. It's exactly how it works. Okay, that's exactly how I came up with the idea of what the electromagnetic wave would look like. And by the way, when it's a particle, it's not electromagnetic. It's not like that waveform I showed you earlier with oscillating electric field perpendicular to an oscillating magnetic field moving through space. It's just particles moving through open space. Now there's two other videos you may want to watch. One's called the candle and one's called the light bulb, which I get into quite a bit of detail about how light is generated. This is natural. The light bulb is a man-made device, but in many respects, at the point at which it's generating light is also very much a natural phenomenon. These streams are not perfect sine waves when they're released, and I'm going to go through this a little bit. I'm going to cover a little bit of the candle, but these streams are what I call messy. Now, in that video about the candle, I showed this slide. This is an actual picture of a candle which shows blue light, red, yellow, white, more red and yellow, and then red at the top. This particular came from another reference, and I'll show you that later, defines the candle in 5 different zones. The wax is melting, vaporizes. With the wick burning, it melts the wax, and then you get these various zones. So let's go through each one. Zone 1 is the non-luminous zone. This is this little blue zone down here. It says there's not enough oxygen for the fuel to burn, so no light. It's kind of trapped inside by the zone 2, which is the blue zone. And there's plenty of oxygen for there. You get a complete burning here, complete burning. And it's you can actually, it's almost translucent. You can see through it. By the way, let me back up. This non-luminous zone is generally about 600 degrees C. Now, these numbers that he quotes look a little bit fictitious. They're all nicely ordered. Don't think a candle is that way, but the point being that this is one of the lowest temperatures in here. When you get to this blue zone, blue is at 800 degrees C. And I was often told when I was younger that the blue flame was the hottest. That's not what it says here. It is the most complete, but it's not the hottest. It burns at 800 degrees C. Zone 3 is the gray area. It's called the pyrolysis or cracking. This is where the hydrocarbons that come from the wax get broken apart and creates minute carbon particles, smoke, if you will. And if that smoke can get out and smoke up your room quite a bit. Temperature is higher at the zone 3, 1000 degrees C. Zone 4 is a luminous zone. The pyrolysis continues due to a short of oxygen, but the temperature is higher and you get yellow or white as shown in the actual picture of a candle. If you're going to get that, you're getting all frequencies out of this one, out of this zone. 1200 degrees C, it's hotter. And finally, you get to zone 5, the veil, which is shown as white here, but also sometimes it's shown as red in the picture. It's at 1400 degrees C. This is the site I got this from. So what you have in the candle is all these different temperatures. Temperature measures heat. And heat, as I have described before, is the vibration of atoms at absolute zero. If you ever could really get there, there are no vibrating atoms. They're all absolutely still. But you never get there because something comes along and perturbs the system and it vibrates anyway. And so the faster, the hotter it gets, the higher the temperature, the faster it vibrates. And so with the blue zone, it's vibrating, and with the with the blue zone, and then it vibrates more, and with red it vibrates even more back and forth. The farther it has to go, the longer the wavelength, the more red it is, the shorter it goes, the shorter the wavelength, and you get more blue. So there is a direct correlation, apparently, between color and temperature. Blue at 800 degrees C, white and yellow at 1200 degrees C, and red at 1400 degrees C. Does heat have something to do with color? And I claim, yes, it does. This is how the light from a candle is generated, and it's not much different in a light bulb. You have particles running through the filament. They hit the filament, and the filament atoms start vibrating, and they get hot. When they're vibrating, if you got the right type of filament, which Edison finally found, and you put the right amount of particles through it, you get the atoms vibrating at the right rate, and you can get white light coming from it because those atoms are pushing out the particles. By the way, it doesn't push out its own particles. The candle, you're losing the particles from the atoms itself in the candle, and eventually the candle disappears. Well, in a you put the light bulb in a vacuum, it doesn't really burn, it doesn't combust totally, it just vibrates and emits particles as white light. Where do those particles come from? They don't come from the filament, they come from the particles flowing through the particles that the electric company provides, even though they say they're not providing it. An interesting thing. You need to watch my video on the hydroelectric dam where I talk about that issue. So combustion is the mechanical vibration of the atom that releases the G1 particle in the candle. In the light bulb, it pushes the G1 particle out. The heat or temperature is based on the rate of vibration, which determines the rate of the groups of G1 particles that are released. They get released when the atom gets hit and it finally breaks apart enough in combustion, it releases a burst. In the candle, it's low intensity. The candle clearly does not give a lot of light. It helps in a dark room, but it doesn't give out a lot of light. But the G1 particles are the G1 orbitals of the atom. And they're released in groups as these particles combust. And this combustion is caused by the mechanical vibration. And the rate of vibration at the time it's combusting gives you the one combusts, it's followed by another one and another one and another one, giving you pulses at some interval. So, but this is my final model. It's not like the triangular wave. It's not like the sine wave. This is I came up with this one much later, where I was actually studying dispersion. And to make dispersion work, you have to get a rainbow. Well, in order to visualize this, this is a small stream of blue light. There are maybe 5 peaks here. There are 5 peaks in the red here. Maybe there's only 2 here. In the green, maybe there's 3 peaks here. You see, as a candle burns, it's very chaotic. It's not going to say, okay, I got to do a sine wave. Do it nice and neat, guys. Everybody together, get it going. In my mind, that's not the way it happens. This is white light in the way I visualize it. And it's visualized that way just because of how the candle might release these peaks of particles. So, white light is messy. Now, it turns out that in an electronic circuit, and I covered this a bit, really nice current or voltage waveforms can be generated. But we're humans doing that. And you can put an electroscope on your circuit and look at that oscillator you just put together, and sure enough, you got this neat sine wave, or you got a very nice, neat square wave. This is based on the flow of G1 particles in a circuit. And you know this is possible. So these are possible that a signal, because you take a signal generator, it can output a sine wave, a triangular wave, a square wave, or a pulse. Or it's programmed to do these things, and we as humans can make this happen inside a circuit. Very neat, very precise. Nature cannot do these precise waveforms. Some sources may come close, but most are messy, especially white light. Just look at the pictures you see artists doing color type pictures of the universe, of the cosmic microwave background. It's messy. It's all based on the objects out there that are emitting particles at lots of different, in particular at the microwave range. Yeah, they're excluding all the other frequencies, all the other wavelengths. They just look at the microwave, and it's messy. But all of them are generated mechanically, and all streams of G1 particles flowing in space or in a circuit all move at or about C. There's in G1 gravity, when I talk about G1 gravity and how it can bend light, it can accelerate light and slow it down. So it's constantly changing. So when we measure speed of light in a vacuum, it may not be changing so much, and it can look relatively constant, but not in the real world. That speed is changing ever so slightly. But there are other types of radiation, Aidan. I just covered electromagnetic radiation. I could go on to another video covering particle radiation, acoustic radiation. Probably never going to cover gravitational radiation. Could talk about cosmic microwave background, which is not mentioned in the list I showed originally. One of the really interesting ones will be black body radiation. Hopefully I get to cover some of these in the future. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.